Ayun, main post. That's it.
Hello, hello, hello. Hello, hello. Can I borrow a mic? Borrow a mic. Can I borrow a mic? Can I borrow a mic? Uh, A3. A3 is it? Okay, okay, okay. 啊，还是不要很远。Can you hear me if I don't have mic today? Because not sure the switch got switched on and then my battery dead. Can you hear me or not from the back? Can I? Okay. I think we should start. I don't want to waste time. Because we need to have a lot of things to cover. It's good that more and more people coming to my office hour now. I think at least 10 of you came already. Okay. Yeah, so I encourage you to come and find me if you have problem. Okay. Please put effort into your assignment, okay? Because assignment constitute most of your score. Okay, and then this is the part also where you learn. And then you get feedback from me. Right. Okay. So please put effort into doing it. Don't just do it, simply do it. Okay. Because you have time. Okay, because you have time, you have resources for you to search for. So don't just treat it like practice. Okay, so do it properly. Just one condition is you cannot copy blindly from the any text or from your friends. Okay, that's all. Okay, so you need to understand, go and search for the answer, understand it, and then write in your own word. Okay, that's the meaning of the assignment. Okay, don't just do it blindly. Okay. All right. Yeah. Any question from previous material lecture tutorial? Tutorial about tutorial, right? So Jimbo is not doing it, then and no one's doing it anymore, is it? Huh? Please do, okay. So if you are a person that need a lot of exercise, please do, okay. And then you can send it to me. Maybe you don't try all of them. At least try a few of them, okay. So yeah, so please do it, okay. No one will I'll say no one will check you anymore, okay. You are grown up adult, so do whatever you need to do, okay. um Anything else? Okay, about the exam. Exam, I think maybe 2 weeks after the 7 or 8 week, okay, we will have an exam. Probably this time, I think, because Thursday classroom is not so good. Okay, either week 7 or week 8. And then I'll see if we can bring cheat sheet. Maybe we can bring a cheat sheet in. Let me decide. Huh? You want to bring a cheat sheet?
Yes.
Okay. No. Okay. Yeah. Yeah, I will decide and then I'll let you know. So similarly, the assignment, right? There's a due date, deadline. There's a penalty if you submit late. Okay, please do it on time. So assignment 2 hopefully will be out this week. Okay, so there are 7, 8, 9, 10. There are 4 questions already leaked from assignment 1, right? So you should do it. Okay, you should do it already. Okay, should be doing it. Okay. There's some terminology in those questions. So I think I wrote. So I think I wrote alternating group in those questions, but I didn't mention what's this group in class. So this is the class I mentioned. This is the group I mentioned before, which is AN. Okay, what is AN? AN is a subgroup of SN. Do you remember what's SN? Permutation group. Okay, permutation of N indexes. Okay, N indexes. Okay. What's this subgroup here? What's the set? This is a set of what? Even permutation. What's even permutation? Huh? Sorry? Sine function. Okay, you can use sign function to describe it, but what's the definition of even permutation? Yes, so these are the permutation that can be written as even product of transposition. Okay, so maybe you ask the question, one permutation can write as even, can also write as odd. So which one you decide? But we prove a theorem, right? Once it can be written as an even product of transposition, it always only can write in terms of even product of transposition. Okay, so even is a property that is how to say that is the how to say so the number of product of transposition that can written by a cycle is an invariant. Okay, it's an invariant. So if it is even, then it is always even. Okay, you cannot somehow even and odd at the same time. Okay, does it understand? Any question? Okay, so yeah, so please please ask question in the class, right? Okay, so I think you have been into 3 weeks of pure math classes, right? So you should know by now that definition is really important. Okay, and then idea flow is also very important. Okay, you cannot just copy, and then you don't know what's going on. Okay, so in my class I offer you, okay, chance to ask. Okay, you can interrupt me. Okay, please interrupt me. Okay, so 如果你不会就要问啊，即刻问。OK，如果你觉得浪费我时间的话，你不用怕。如果我觉得你浪费我时间，我会把你暂停。OK，Yeah，is it okay or not? Okay, so don't worry that you will waste my time. I will stop you. Okay, but the very important in this understanding this abstract hard definition or proof idea, right, is sometimes you think wrongly. Okay, just that you think wrongly. Okay, so if you can correct at the same time, then the idea will flow easily. Okay, yeah. So the difference between hard and easy is just a thinking change. Okay, just a thinking change, just a change of thinking. Then you will feel easy. Okay 了 ，please ask 请问问题Okay, this is the things that I've focusing since last semester. So please. But I can see that some of you start changing already. This is a good sign. So please keep it up. Yin Ke, is it? Yin Ke, have you submitted your assignment? Why not? It's due already. Have you done your assignment yet? Please submit on time. Otherwise, you'll get penalty 3% each day. Okay? Yeah. Please do it on time. Okay. Okay, another terminology I want you to familiarize is this. What's the bracket of some element here means? What does this mean? Generating set. Okay, so this is a generating set of what? Generating set of what? How to generate what? The smallest subset. Okay, not enough. So this is a smallest subset containing A1 and 3. Good. And then what kind of subset we are interested in? No. Cyclic is what? Yeah, cyclic is good, but cyclic is just generated by one element. Okay, here got 3 elements. So what's this? Yeah, generators. Generators of what? Generator of what set? What kind of set? What kind of set we are interested in this course? In this course, what kind of set we are interested in? Group. Okay. So this is the smallest group. Okay, generated by these three elements. Okay, we are interested in group. Smallest. So smallest groups means what? These have to satisfy 3 or 4 properties, right? Okay, what kind of properties? Okay, so let's say, so it's a smallest subgroup, okay, in G containing A1, A2, A3. So close. So first of all is closure. Okay. And then 2, identity. And then inverse. Anything else? Sorry? Associativity. Okay. Okay. So so this is the thing you prove in the assignment, right? Okay. So as long as you have an induced operation and then your set form a group, then it is a subgroup. Okay. So you see, I didn't put identity here. Right? I didn't put identity in this set, but identity is always in the set guaranteed by the property of subgroup. Okay. We only care about subgroup generated by these 3 elements. Okay. So meaning A1 is in there, A1 inverse is in there, A2 inverse is in there, A3 inverse is in there. So when they compose, E has to be in there. Okay, because we want the closure to happen. And then we can compose anything inside here. And then the closure have to, the product of all these generators have to stay inside. And then the inverse of this product also have to stay inside. Okay, to form a smaller subgroup. Okay or not? Okay. So it's like you have some building block, but this building block have to satisfy group property. So you keep adding in, add until you just get enough to get a group. That's all. Stop adding in already. Okay. Okay. Don't add extra stuff. Okay. Meaning, you understand? So don't need to add extra stuff other than making the 3 generators a group. Okay. So we call the smallest subgroup. Okay. It's the smallest one. Okay. Okay. Okay, so these are notation. Okay, good. So where did we stop last time? So we stopped at a group homomorphism. So what's a group homomorphism? A map, okay? It's a map between what? Yes, a map between 2 groups, okay? So what's special about these maps? Okay, so what we call this is called the multiplicative property of a map, okay? So it preserves the multiplication, okay? Phi of AB equals to phi A times phi B, okay? And this is true for all AB in G, okay? So remember I told you how you memorize this property. How you remember this property? No. How to remember this property? Diagram. What kind of diagram? Commutative diagram. Okay, commutative diagram. Okay, so commutative diagram, what do you have? You have G to G prime and then G to G prime. Okay. So first of all, you take AB from your G. Okay. And then you can map it across. Okay, not that I have a arrow difference here. Okay. So if I have these like a hook, is it a hook arrow here? And then I am sending the elements. Okay, if I have a normal error, this is a map. Okay, so A, B here will get sent to, let's say here is a phi map, so we'll get phi A and phi B respectively. And then between G and between G, okay, we can put a multiplication here. Okay, so maybe to be precise, right? To be precise, let's do it as a product group here. Okay, so we are considering a pair of elements. Okay, and then if we multiply, we will get AB at the bottom. And then we also do multiplication on G prime, on the product set of G prime. And then we will get PA dot PB. Okay. But we keep the horizontal map the same. Okay. So the top here by right, I should put something like this. Okay. And then I put phi on the bottom. And then what phi does to AB is to just send phi AB to phi AB. Okay. So a priori, these two things don't have to be the same. Okay, because you do it in via different roads. But for phi to be a group homomorphism, they have to be equal. Yeah. Okay. Yeah. So if these two roots coincide, we will call this a commutative diagram. Okay. So the diagram commute. Any question? Please ask. Please ask. Okay. So this idea is kind of abstract. So you never seen it before. Okay. So please ask if you have any question. Also, I encourage you to do pre-reads before you come. I put some section on the Moodle you can read first, and then you come. And then maybe you can bring some question when you read. Okay, bring to the lecture. If I don't answer your question in the class, like when I'm teaching, then you can just ask. Okay, I was confused this part when I read it. Okay, you just ask. Don't be shy. Okay, everyone okay with group homomorphism now? Okay. So last time what do we have? We established some property on this group homomorphism. Okay. So phi of a bunch of product, we can just split into product of phi of AI. Okay, so this can be done by induction. Okay, you know how to do on 2 elements, then you can do on n elements. Okay, finitely many. And then phi is very special. Okay, what phi does is phi sends identity to identity. Okay, phi sends identity to identity. So it's kind of quite restrictive in this case. Okay, group homomorphism is quite restrictive. It sends identity to identity. You cannot send identity to other things. Okay, and then another good thing is it sends inverses to inverses. Okay, so inverse operation commute with phi. Okay, send inverse to inverse. So A inverse is a inverse in G, but phi A inverse is an inverse in G prime. Okay, so this is how you should read it. Okay. Okay. Let's start a new stuff today. I think at your level, right? So you are second year now. So before proving a theorem, okay, please understand the statement of the theorem first. Okay, understand the statement of the theorem. Understand what's the proposition doing. before you prove is more important now. Okay. Otherwise, if you read the proof, you might not get anywhere. Okay. So please understand the statement first. If you already understand the statement, you are already halfway through the proof. Okay. Understand the statement is already halfway through the proof. Okay. So let's do definition. So we have a map, right? So for a map, we can consider the image and the kernel. So let me remind you what's the image of a map. So what's the image of a homomorphism? Okay. So image of a morphism is let me write down, is denoted by phi of G. Okay. So what does it mean by phi of G? So phi acts on phi takes value, takes in input of the element in G. Okay. So why do I write a group? So how phi takes in a group? Meaning what? Meaning phi takes in every element in the group. Okay. So this is a shorthand notation. So what's this definition here? Phi of G is equals to image of phi. Okay. So image of phi is defined before. Okay. So this is just a image of the map of set. Okay. So let me write down. It's denoted by and is the image of P as a map of set. Okay. So why do I define by image of a map of set? What's a group? Group is a set with a operation. Okay. So in particular, this map have to tell me what happened to the set. Okay. What happened to the set? How about the operation? The operation have to respect the multiplicative property just now I showed. Okay. So image of P is what? Is all the element in the codomain such that it is mapped by the phi. Okay, so if there exists some A such that phi A equal to X, then X is in the image. Correct or not? So you need to have a picture in your mind. Okay, I have a G. I have a G prime. Okay, I have a map called phi. Okay, I have a map called phi. So where are the image? Okay, so phi maps everything to an image. Okay, so maybe map like this. Okay, we call it phi G. Okay, phi G. Okay, so this X is coming from some A. Make sense? Okay, so if phi G equals to G prime, what do you call that map? Onto, okay, or surjectivity, subject to the codomain. Okay, please recall. Later we'll keep using these. For example, remember we have a map from Z plus to G. Okay, what's this map here? So this map here is sending A to, oh sorry, just use N maybe, N to A to the N. Okay, and what is A? So this is a fixed A. So this is a fixed A in the G. Okay. So what's the image of this phi A? So you map positive integer to AN. Huh? Is it actually G? No. I think we need to throw away this. Just consider every n. What is this? What do you have in your image? What do you have for your z? Minus 1, 0, 1, 2, 3, 4, 5, 6, 7, and so on. And then you get a to the all these power. So what are these? So you get a minus 2, a minus 1, a 0, a 1. Okay, I want to ask a person. Ellie, what's this image? What's this image? Uh-huh. Ellie. A minus n. What's a minus n? A minus a. Sorry, a to the power of minus n. What's this? A to the power of n. Okay. So this is the map, right? This is the map. So what's this image here? Can you recognize what's this image here? Yeah. So this is a generating. This is the. This is equal to the generating set by A. So I mean, generating set is not enough. Okay. Generating set is just generate. Like how much you want to generate. It's not enough. This is the group, the smallest subgroup. Okay. So this is the smallest subgroup generated by A. Or in another word, what is this? This is a cyclic group. Wait now. So this is a okay. So this is the cyclic group generated by A. Okay. Yeah. So generating set is not enough. How much you want to generate? Okay. So yeah. Question? Yeah. Why not just include all the? What do you mean? Oh, because I only pick one element in G. Fix one element in G. Uh, so I fix. Uh, so I fix A in G. Okay. And then my map is a fixing A. Okay. A is fixed. A is fixed here. Okay. And then I consider all the power of A. Does it make sense? Yeah, the image set. Yeah, yeah. It doesn't equals to whole G, but depend on what G you have, right? Depend on what G you have. If your G is a cyclic group, and then your A is the generator, then maybe you get back the whole G. G G is not fixed. I mean, wait. G is fixed, but depend on what G you have. Yeah. So if your G is not cyclic, right, then definitely you won't get back your G. But if your G is cyclic, then you can get back your G by just choosing A to be the generator. Yeah. Any question? Okay. Yeah. Okay. So from here, what you can see, what can you observe here? Okay. Actually, you observe that the image of a homomorphism is a subgroup. Okay. So let phi be. So let me simplify it. Okay. Put a homo here. So if H is a subgroup of G, then phi of H is a subgroup of G prime. Okay. And if K prime is a subgroup of G prime, then the inverse of K prime is a subgroup of G. Okay. Okay. So do you know what's the definition of inverse here? Let me put down these. Recall on your set theory again. Okay, so definition. The inverse image, and phi inverse of K prime. Okay. So let's start with a map, right? So let's start with a map first. So let phi from G to G prime be a map of set. Okay. So you see, I go between map of set and homomorphism. What's the difference here? What's the difference between homomorphism and map of set? Yes, one of them have one preserve the multiplicative structure. Okay, the other is just simply a map of set. Okay. In particular, all the homomorphism are map of set. Okay. So what's the inverse image of phi inverse? Okay. So let me see. Okay. So the inverse image of G prime, okay, is the set. What's the set? Is set. So let me write yeah, let me write it down. So what's this set here? So what's the inverse image? So so where does this element have to live? So phi is a map from G to G prime, right? Okay. So phi inverse. Where do you think the element should live? It should be something in G, right? Because inverse, okay, inverse, the word inverse and the sign inverse here suggesting we have to go back. Okay, go back to where? Go back from the codomain to domain. Okay. So in particular, we are interested in some element in G. Okay. So what does this element has to satisfy? What does this element has to do with phi? Inverse phi inverse phi x equal x. Let me see what's this doing. So you send phi across, okay, and then you come back. So okay, first of all, I don't want to care about what this is doing first, but this inverse here I haven't defined yet. So why you put into, so I'm defining something I want to define. I'm defining something using what I'm defining. Right. So this doesn't work. Okay. This is a bit similar to your assignment question. I asked you to prove delta is invertible, but you already start using delta inverse in your question. Okay. After I mark, I will give a summary feedback. Okay. Don't use things that haven't been defined before. Okay, or proven before, or you want to prove. Okay, you cannot assume them. So what do we have here? So what should we put here? Again, inverse is not defined yet. Why you put inverse into your definition? You get what I mean? You get what I mean or not? So you are defining something you want to define. But you only know about phi. So you need to use this phi to define your inverse image. Px equals to what? Belongs to G prime. Yeah, let's see. So what's this saying? X in G, phi x in G. This is normal. I don't think this is saying anything about this particular image here. Huh? X. Yes, this is the whole G set. Yeah, what you say is the whole G set. Yeah, because. Oh, okay. So yeah. So let me see. Okay. No, I describe you a situation. So we have a map from G to G prime. Okay. So what I do is I map every G across. Okay. Like what I said, maybe you don't reach everything in G prime. Okay. And then now the inverse, what does the inverse do? The inverse have to send everything back. Okay. But you can see that what can you do with these other stuff? What's the inverse image of this guy? Nothing gets sent to them. Okay, so their inverse image should be just empty set, empty, just empty. But for the others, how do we define this? Surely, if you go back, they are all in G. What have you learned in your discrete math? Let me tell you, discrete math is not this easy. I never took discrete math in my undergrad, I learned throughout my undergrad year. Then I don't think discrete math is easy. But what's the inverse image? Hmm? So Li Kai say inverse image are all the element in G such that phi x is in G prime. This is okay or not? Okay. No, okay. Huh? Match this picture or not? Does it match this picture? Does it match this picture or not? Match, huh? Cannot decide. All the x in G, okay, such that phi x is in G prime. Okay. 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 Correct or not? So phi x is in G prime. Okay. Okay. So you see here, in particular, phi inverse here is what? It's not a map. It's a set. Okay. So this is a very important difference between phi inverse as an inverse image and as an inverse. Okay. Inverse and inverse image is different. Inverse is what? Inverse is an element in the group. Okay. Inverse is a invertible element. Okay. Invertible element, that means you compose with phi, you get identity. But inverse image is not a function. It's not an element. It's a set. Okay, it's a set. Okay, this is very important. So when we look for inverse image, what do we mean? We mean that we look at the image of my map, and then we see what elements get maps into the image. These are all the inverse image. Make sense or not? I look at the image, the inverse image gets sent to the image because I reverse, so I inverse the image. Can or not? So I got the image. Okay, I got the image, and then I inverse it. And then inverse image gets sent to image. Okay, that's why we have these two terminology: inverse image and image. So inverse image are the things that get sent to the image of phi. Understand? Can. So inverse image are the things that get sent to the image of phi. Okay. So you need to be able to relate inverse image and image. Okay. What are inverse image? All the things that get sent to the image. Okay. Okay. So yeah. So let's come back. Okay. So which one you guys want to prove? Let's pick one of them. One or two. Both. Okay, pick one first. Number one. Okay. Let's try number one. Okay. So proof. So suppose, yeah. So suppose, okay. So suppose phi h is a subgroup of G. Okay. Then we want to show, what do we want to show? Yeah, sorry. Good not getting not smooth now. So phi of h. Okay. So we want to show this. So to show subgroup, what are the properties you need to show? So first you need to show closure, right? Okay. And then you need to show identity. And then you need to show inverse. Okay. Okay, right. So closure. So meaning if I take two elements from VH, okay, we need to show that AB is also in VH. Okay. So this kind of proof is very easy. You need to just go back to your definition. Okay. See what's the definition for your condition. See what's the definition, what you need to prove. Okay. So let me show you this magic here. Okay, let me show you the magic here. Yeah. G prime. Yes, G prime. Sorry. Yep. Okay. So what's the magic here? So state the definition. What's the definition you have? Okay. So AB in VH means what? Means that there exists A prime, B prime, such that phi of A prime equals to A, phi of B prime equals to B. Is it okay? Or do you guys familiar with the definition of image or not? The image is the set of what is image? All the elements. Let me write B H G go to G prime. It's the set of what? Set of all elements in where? So you map H across. Okay, so these are elements in G or G prime. Phi H. Huh? G or G prime? G prime. Okay. So all the element in G prime such that what? It's like phi H. Looks like phi H. Okay. Meaning what? There's some Y prime. Okay, maybe I put prime here to match my G prime. There's this Y in G. Okay. So phi H, how to remember phi H? Phi H is something that looks like phi of something. Okay. So phi H is all the things that looks like phi of something. Okay. You get what I mean? So picture again. So picture is very important. In mathematics, right? Actually, symbol is not so important. Picture is important. This is why I talk about intuition. You need to have the right picture in your mind. Okay. Why we put a lot of symbol? Symbol is just for communicate. Tell people what is that. Okay. So what is the picture you need to always keep in your mind? G and G prime. Okay, G and G prime. And then you have a map phi. Okay. So what is phi H here? Okay, so what's phi H? So you have a H, okay, and then you map it across. And then this thing is called phi of H. Okay. So in particular, what does this mean? So every element in H here, so let me zoom in. So every element in H, X, Y, Z, okay, they are get sent to phi X. So phi X, phi Y, and phi Z. Okay. So this image looks like phi applied to some element. Okay, so this is what I wrote here. All the element in G such that it can be written as phi of something. Okay, meaning it comes from somewhere. Okay, so these elements are coming from somewhere. So this is an image of my map. Okay, make sense? Make sense or not? So this is the two key things you need to remember in for this 2 hour here. Yeah. Okay. Because we'll deal a lot with these image inverse image. Okay, so this is one part. How about the other part? How about the other part? So we have our property, we have our assumption already. How about our goal? What's our goal? We want to show that AB is in phi of H. Okay, so what does it mean by that? So let's put our goal first. So in mathematics, right, goal is very important. Okay, because you might lose in the middle of proof. Okay, so how you pull yourself back? You need to always remind what's your goal. What's your goal? What's your goal? What's your goal? Okay, if you are not approaching your goal, throw the method. Okay, do it again. You need to memorize what you need to remember what's your goal. Okay, our goal here is to show that AB is in phi of H. So this means what? We need to be able to find some call it what? Call it W, such that phi of W is equals to AB. Okay, you need to find something that gets sent to AB. Okay. 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 So start from our assumption again. So fix A and B in pH. Then we have phi of, what do I call? I call A prime. A prime. And then equals to A. Phi of B prime equals to B. Okay. So you see, you got AB here. You got A and B. What can you do? What can you do? You got AB. You want A times B. What can you do? Huh? Multiply. Multiply both of them. Okay. So note that A dot B is what? Phi A prime dot phi B prime. Okay. But you want phi of something. But here is a product of phi. What can you do? Huh? You can use the definition of group homomorphism, right? Because phi respect the multiplicative structure, so the product becomes phi A prime dot B prime. Okay, so you get that phi of something equals to AB. Then this is the something that you are looking for. So now define W equals to A prime dot B prime. Then you are done. Okay, then we are done. Okay or not? Okay. We found phi of something equals to AB. This is what we want to find. So it's actually the product of my inverse image. Okay, product of my inverse image. Okay. Make sense? Make sense? Okay. So you want to try another proof, is it? If we prove this, can we shorten the recess time or not? Can we shorten recess time to 5 minutes? Can or not? I can do extra, but we still need to cover stuff, so need to balance a bit. Is it okay? No, okay. Huh? No, okay. Okay. I will do once now, okay? In future, right? We cannot do similar stuff few more than one, okay? Because what I want to say is this part 1 and part 2, right, will be proven similarly, okay? Usually in the practice of maths, right, we will do one of them and then the other one will let you do exercise. Okay, you need to use the similar concept to do it. Okay, so because this is the still quite new, right? So okay, we will do all of them, and then in future, I will leave similar proof as exercise. Okay, when I say left as exercise, that means it is similar. Okay, so you use a similar idea. So let's see how these two are similar. Okay, so I'll demonstrate to you why these two are similar. Okay, so if G prime is a subgroup of K prime is a subgroup of G prime, we want to show that inverse image of K prime is a subgroup of G. Okay, so we have our assumption and our goal. Okay, so what's our goal? So we want to show that the inverse image of K prime is a subgroup. Yeah, it's a subgroup. Hey, are we done yet? Actually, we haven't done, right? The subgroup just now. So let me rewind first. So a bit too excited already. So we haven't finished the other two property. Cut. Okay, so okay, so what we haven't done, this is just closure. So how about identity and inverse? Okay, so the question is, does there exist an identity? Does there exist an identity? Identity in phi of h? Okay. Does there exist an identity in phi of h or not?
Yeah.
Huh? Sure. Okay. So what does it mean? So does there exist an x in G such that phi x is equals to 1? Okay. So what's the x you need to take? Just take the identity of, just take x to be the identity of G. Okay. Here is G prime, right? So our phi f live in G prime. Okay. This is guaranteed by what? Guaranteed by what? Why identity of G must go to identity of G prime? This is guaranteed by what? Huh? Yeah. This is guaranteed by the property of group homomorphism. Okay, because we start with a group homomorphism. Okay, group homomorphism but must send identity in G to identity of G prime. Okay. Okay. Yeah. How about inverse? So for every A, so for every Y in PH, okay, there must exist a Y prime in PH. Okay. So how? So let's write down. Want to show. Let's write down what we have and what we want. So this is what we want. Want to show that for every element in PH, there's an inverse. Okay. So how to find these? So how to find these? You need to open out the definition of this phi h. Okay, what's the definition of phi h? If y in phi h, that means what? There exists y prime in h such that y equals to phi of y prime. Okay. 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 So okay. So do you have idea or not? Yeah, use the property of homomorphism again. Okay. So how to use? So what's the y prime you suggest? Identity? Identity, yeah. You suggest this? These are identity. So does this satisfy or not? Okay. So 1 times y, you still get y. But inverse is the thing that you when you multiply to y, you get identity. Okay. But 1 identity times y is always y, not identity. Okay, so we don't want identity. What do we want? What do you want? We already have y, right? We already have y. And then y have a form, phi y inverse. Okay, maybe you just guess I want to put an inverse here. How about I put an inverse here? Is this defined or not? Does this inverse exist or not? Exists, right? Because phi y prime inverse, phi y prime is an element in a group. So in the group, every element has an inverse. Okay, so in particular, this guy exists. Okay, this guy exists. So I can just define this. And then we check whether it satisfies the inverse property or not. Meaning, does it satisfy y of phi of y prime inverse equals to identity? And I swap it. The left and right inverse, does it satisfy? Okay, does it satisfy the left inverse and right inverse property? Make sense? Make sense? Please recall the definition of inverse. Okay, recall the definition of inverse. In particular, this is what you want to check. Or if you cannot accept so many symbols yet, so let's see from here. Okay. Okay. Remember, can recall the definition of inverse here. Okay. So how to verify this? How do we verify that? Just now, Ying already tell you the answer. How to verify it? How to check? How to check? How to check? How to check this second line here? What is y? P of y. P of y prime. So is the third line true or not? True, right? Okay. So this is true because we pick the inverse. Okay. But okay, so this is true. So but you need to be careful a bit here. Okay, be a little bit careful here. This definition, right? This definition. Is there any problem with this definition or not? Is there any problem with this definition? No. So you see, this definition is, there's a little bit problem in this definition. Okay, you know why? You fix a y. Okay, this y prime, right, can change. It just said that exists. Okay, that exists. Okay, so seems like this definition, is it well defined or not? Don't know. No, why no? Is it well defined? Yes. Why? It exists for all y. Not quite true. I mean, no. I mean, I fix a y. Okay, I fix a y. There's a lot of fy prime. Right? So is this well defined or not? Let me think how to say this. What kind of morphism we have? Yeah, I mean, is it well defined? So if I have a y, right? Say I have a y prime 1, y prime 2, get mapped to the same y. Okay, so maybe I take phi of y prime 1 inverse and then phi of y prime 2 inverse. Any difference or not? Why? Any difference? Why not? What's the property you use? What do you mean? Yeah, inverse property. Yeah. What kind of inverse property? What's the inverse property? Uniqueness of inverse. Okay. So in a group, every inverse is unique. I think we proved this 2 weeks ago. Yeah. Every inverse in a group is unique. Identity is also unique. Okay. So in your group, there's only one identity. Okay. And then every element also only have one inverse. Yeah. Okay. So yeah, so you need to be careful when you do this kind of proof. You need to check whether your definition is well defined or not. Okay. You need to check your definition is well defined or not. Okay. Any question? Okay. Yeah. Any question? Okay. You need to check well defined when you define stuff. Uh. Yeah. Okay. So yeah. Any question before we proceed? No. Huh? Yeah. Simple got question No, say lah. Just say anything. Y prime is in VH. P Y prime is in VH. And then if Y prime is in VH. Yeah. Why can I directly take the? You mean why can I take this inverse? Oh, okay. I get what you mean. Okay. Yeah, correct. Okay. So, so what? Wait, let me think. Okay, so my argument just now is my phi y prime is in G prime. Okay, so in particular, phi of y prime inverse exists in G prime. Exists in G prime. Okay, but we want to show whether phi y prime inverse is in phi of h or not. Correct, correct, correct. Okay, correct. Okay. Okay. Does everyone get this? Okay, so Jimbo say, okay, I know the inverse is in G prime. Okay, but why does inverse have to live in phi h? Phi h is a subset of G prime. Everyone got this? Yeah, why? Who? Huh? Okay. Okay. So we are not quite done yet, right? So we still need to show. Okay, so we still need to show what? So we still need to show. So this one. So we define this. Okay. So first thing we check invertibility. Okay. The second thing. So the second thing you need to check is whether phi of y prime inverse is in phi of h. Okay. So this is the second thing you need to check. Okay. So to check this, so Ning, what did you say? Something. Okay. So meaning, okay, you already said the answer, but what you want to do is, so there exists some w such that phi of w equals to phi of y prime and then in inverse. Okay. Then who is this w? Should this w be? W in where? W in the domain. Okay, so who should this w be? Huh? You just take w to be y prime inverse y by group homomorphism or by the property of group homomorphism. By the definition of group homomorphism, phi of y prime inverse is phi of y prime everything inverse. Okay. Is it okay? Phi of something equals to the inverse of phi y inverse, y prime. Okay. Can. So the property of group homomorphism is quite important. Okay. Yeah. Yeah. Really well. Yeah, we already get the inverse, right? Because first it satisfy the inverse property. Okay. Satisfying inverse property is quite obvious, but why is it in phi h this inverse? Okay, because we can find something that get mapped by element in element in H. Okay, in particular element in H, not just in G, or this is not just in G. This has to be in H, right? Because what? Because you have to write as phi H. Okay, and Y prime inverse, is it in H or not? Y is in. So let me complete it. Yeah, so there's a lot of details going on. So since Y prime, okay, is in H, and H is a subgroup, then Y prime inverse is also in H. Yeah. Yeah. Y prime got inverse, Y prime is got inverse, and then phi prime is yeah. And then wait, repeat again what you're asking. So what's the issue here? What's the y equals to phi y prime? Yeah. And then
If I can show you what my version of
if we show that phi prime got inverse, we are done. Here, yeah. So okay. So what are we showing? So you see, what we want to show. So for every y in phi h, okay, we want to find an inverse in phi h. Okay, so there are two things here. One, you need to find inverse of y. The other thing, you need to show this inverse is actually in phi h. This is what we are doing just now. So we want to first find the inverse, okay, and then show that this inverse actually live in phi h. Make sense or not? Make sense or not? Does it make sense? First, we want to find inverse for every y, and then we need to argue that this inverse is actually in phi h. Meaning you can write in the form of phi of something. Okay, so yeah. Better now? Better. So we have shown two things, right? So one thing, so first I define what is y prime, y inverse, and then I check whether this satisfies the inverse property or not. Okay, so we got the y inverse. And then I need to write this in terms of phi of something. So phi of what? Actually, it is just phi of y prime inverse. Okay, phi of bracket y prime inverse. And then this is phi y prime bracket inverse. And then why are they the same? Because of definition of group homomorphism. Okay, group homomorphism inverse commute with group. Okay or not? So it is this one. Okay, so commute inverse commute with the group homomorphism. You can bring the inverse up. Okay. Any question? Hey, so you guys need to be a little bit observant here. So why I don't put phi inverse here? So it's a different thing. So it's really different thing. So this is actually phi A bracket minus 1. Okay. But you see, just now so many bracket looks a bit messy. So you need to know what is going on. Okay. It's not. I don't want to say equally. Okay. Question. Question. Let's take a break until 10:30. 10:30.
你这个是你写过的
啊？怎么嘞？
？OK，这我跟你讲，就是
对啊，
这个很好，这个很好，可是你写到最后，忘记这样的。
那这几天都是这样。
我不懂刚才看了这个题目，
我已经，你一开始点的时候，OK，这一边一开始，但是你会发现，你会一直想要多了，越来越不东西，然后如果你要就 overload 了
OK，
就是
OK，
现在跟你讲这个吧，
OK，
然后你东西越来越，你已经觉得有点看不清了。
OK，
就是这样跟你讲。
OK，可以。
对，我最后你再听，我已经在那里看到了。就符号太多了，对，可是可能分几面就他们至少给他们就给别人。我
知道。可以。OK，Thank you。
OK，看下去。
什么？
对，就刚才那个 inverse image 来，对啊，inverse image 只可以是黄色这样子整个 map 过来，然后如果是像橙色这样子的话，我只可以把这个弄 inverse image，没有办法把整个取出来。
可以，就是说，如果没有的东西，它那个 inverse 那个 set 是一个 empty set，没有东西被 map 进去。OK，其实那个 inverse image 要 define on 一个 element 先，就是说，应该比较好 start from 一个 element，就是definition。OK，so 我有一个 map from G 去 G prime，so 放一个 prime 在这里了，so inverse image of x prime 是所有的东西 x in G such that phi of x 等于 x and then 我们就扩张成一个 set， 扩张成一个 set 就是说，像刚才这个就是说 as long as 你的 phi x 是活在这个 G prime 就好，你只要这个 phi x 是等于某个东西在 G prime 就可以，所以这个 s prime 就扩张成全部。这个 set 可以是 empty， 就是说，假设这个你选这个点，我这个 map 的话，没有东西被 map 过来嘛，所以这个 set 就变 empty 去。所以如果你看这整个的话，它可能是一个 empty set、empty set、empty set 加上这个，其实就是加上它。
刚刚就看，这个黄色的跟那个平卡的，对，看那个同学，我故意把那同学，
哦，OK，OK，OK。所以我的 argument 是来，因为如果我有一个y 在 VH 里面 ，OK，我就会写成 y 等于 Vy prime 嘛，对，
这个明白。
把这个 y 是活在 G prime 里面，对，y prime 是活在 G prime 里面，and then Vy
map from
yeah，so in particular G prime 是一个所以它是一个 group 的话，每一个 element 一定有一个 inverse，这样我就可以 take 这个 inverse 哦。but 的问题是呢，我们要说的是 VH 是一个 subgroup，意思说这个我选的这个 inverse 一定要活在这边，OK，然后这个就是我们第二个在做的 part，就是它是 phi of 谁，yeah，然后 by group homomorphism actually 你就是 take phi of 那个 y。
如果你加一个空闲的，也可以加它的 application in physics。
application in physics 啊
？Yeah，
不要看一下，我应该有 example 的，我会给 example，我给 example，yeah，我会给 example，我会给 example，我会给 example。
对吗？in hash，然后这个东西 in free hash，这个 in hash 的话，这 in hash 的话，这个东西 in free hash。
呀，什么 email 吗？什么 email？什么 email？啊？看一下，什么来的？
sorry 呀，等一下，
啊，then
全世界走到这个
what？
你是
没有啊，我没有啊，
你是手臂有那什么吗？
我注册我没有啊，
你注册哪一个账号先？
我忘记了。
所以，OK，sorry，
原来还 get 到我们全部的 data。
这个
哎，等一下，下次
OK，
要开始了，慢一点啊。OK，so yeah, seems just now we spent quite a lot of time on that proof just now. So maybe can you try this at home for the inverse one? And then if you have problem, then we can do it on first day together if you like. Okay, I'll let you think a little bit. Okay, try and think a little bit. Okay. So today we got a physics student with us. Actually, this course is quite related to physics. How to say? Because the latest model called the standard model of particle, standard model for quantum physics, is based on group theory. It's based on group theory, or more precisely, it's called representation theory. Okay, so it's based on group theory. So surely these have application in physics. Okay. So I'll try to see if I can put more example into this physics stuff. But as for this theorem we have proved here, okay, what does this say? Okay, this says that group homomorphism is not useless. Okay, it's not useless. It's not useless. Why? In particular, why? Okay, you can look at the group. Okay, and then you take a lot of subgroup. Okay, you take a lot of subgroup. So this homomorphism sends group to another group G prime. Does it respect the structure of the group or not? Okay. Last time we said that every cyclic group have a cyclic subgroup. Okay. So every subgroup of cyclic is cyclic. So you map a subgroup across. What is it? Is it a random set or not? It's not random. It's still a subgroup. Okay, subgroup of the whole domain group. Okay, it's a subgroup. Okay, you don't send to a random stuff. You send subgroup to subgroup. And then the second one is what? If you start with a subgroup in G prime, okay, and then you take the inverse image. Okay, not that this is inverse image, not inverse function. Inverse image. Okay, it's still a subgroup. Okay. Yeah. So how you realize in physics, these group elements you can think of a particle. You combine two particles, you create another particle. So this is like group element. A times B gets C. Yeah, you can think of it that way first. Okay. Okay. Yeah. Okay. Maybe we'll say more again next time. Okay, when we see more structure coming out, and then we will try and relate. So next important things in the map is the kernel. What's kernel? Kernel. Yeah, the set of things that get sent to identity. Okay, is 0. 0 is the identity of the set. Okay, good. So let me put the setting up again. Let phi from G to G prime. Okay, and then identity in G prime. Do you wonder why this is called kernel? What's kernel? Do you know? Kernel is the thing inside the nut, right? What's nut? Nut. No, it's okay. Nut is easy. So nut is just you know, the snack you eat, like peanuts, whatever nut, those are nuts. How does nuts look like? How the nuts look like this, right? So this looks like what? This looks like what? What does this look like? No dirty stuff. What does this look like? Okay, what does this look like? 0. This looks like 0. The things inside the nut is called kernel. So you see, phi of A equal to identity. So you send something inside into the nut. Okay, so we call this a kernel. Can or not? So you got a 0. Okay, last time you see it as a 0, right? So this is a nut. And then this is your kernel. Okay. You send the kernel into 0. Okay. Can or not? Kernel, nut. Okay, proposition. So a very important proposition is the kernel is a subgroup. Subgroup of G or G prime. Subgroup of G or G prime. G. Okay, good. Because they are element in G. This property is very important. This gives you a way to create subgroup. So whenever you see homomorphism, okay, you take the kernel, it will form a subgroup. Similarly, you see, same exercise. What do we want to show? Closure, identity, and inverse. Okay. So how to check closure? For every A and B in kernel of phi, okay, we must show that AB is in kernel of phi. Okay. Can you see why is it true? Can you see why is it true? What is phi of AB? Phi A times phi B. But phi A and phi B are in the AB are in the kernel. So phi A and phi B are just identity. Identity times identity is identity. Okay, so in particular, AB satisfy the property of the kernel. Okay. How about identity? Is identity inside the kernel or not? Yes, right. Because by the definition of group, not definition, but property of group homomorphism. Okay. What I want to write is 1G is in kernel of phi because phi of 1G is equals to the identity of G. Okay, how about inverse? Inverse. So for every A in kernel of phi, okay, we must show that there's this y such that ya equals to, sorry, we want to show what? We want to show that yeah, correct. So such that ya equals to identity in G equals to ay and y is in kernel of phi. Okay. So the obvious candidate is who? The obvious candidate here. Who is the obvious candidate here? Who is the obvious candidate here? So you need to check two things, right? Like just now, we want to find some inverse to y, and then we need to show that this y is in the set we're trying to show is a subgroup. So what's the obvious candidate here? What should we take for y? A is in the kernel of phi, but kernel of phi is a subset of what? G. Okay. So the picture you want to keep in mind is G prime. Okay. And then you got a subset. Okay. Now subset first. Subset kernel of phi. Okay. So in particular, you are an element in G, right? So G is a group. So we can take Y to be inverse. Okay. So the next job is to show that to show that phi of A inverse is actually equals to identity of G prime. Okay, to show what? To show A inverse is in, to show A inverse is in the kernel of phi. Okay, so why is this true? How to use property of group homomorphism here? Okay, so maybe we'll start from the left hand side. Okay, and then what we can do is we pull the inverse out, and then okay, so we know that phi A is in the kernel, which means phi A is just the identity of G prime. So what's the inverse of identity of G prime? It's just identity of G prime again. Okay, so the first part is by property of group homomorphism. Okay, then second part, yeah, is by the inverse of identity is a identity itself. Okay, inverse of an identity is identity itself. You guys know inverse of an identity is identity itself. What is the thing that multiply in identity equal identity? Identity. Okay. Yeah. Okay. Okay, so this is very important technique. Show some subset is a subgroup. Okay. So I can change the property of the set and then show that something is a subgroup. Okay, good. So let's look at some important definition now. Okay, so for example, so last time we looked at a determinant function. Okay, so GLNR. Okay, so this is a very important group in physics. Okay, this is GLNR. So this is an n cross n invertible matrix. Okay, this forms a group. Okay, but in physics, more significance is this is a Lie group, Lie algebra. Lie group. Sorry, Lie group. Okay, it's the Lie group. Okay, for the physics part. And then, what's the kernel of this thing? What's the kernel of this? So to find the kernel of a map, right? So kernel means what? You need to map elements to identity. So what's the identity in R cross? Yes, 1. So what are the things that get maps to 1 after you take determinant? So this is a set of n by n invertible matrices with determinant 1. Okay, last time we talked about this matrix. It's called a special linear group. Special linear group. Okay, so this is another important Lie group. Okay. Yeah, so this is SLN, and then second, let's look at the sign homomorphism. Okay. So sign homomorphism is also a group homomorphism. So how is it the right hand side a group? +1 and -1, how to become a group? How is it a group? Okay, what's the so group, right? You need to tell me operation. So what operation you want to put here? Yes, multiplication. Because 1 times -1 is -1, -1 times -1 is 1, and then 1 times 1 is 1. And then 1 is the identity. So everything is in there. Inverse, identity, closure. Okay. So This is a group with multiplication. So what's the kernel of this group? Yeah, set of all the even multiplication. No, set of all even permutation. Okay, so what are this set here? What is it called? This is called the alternating group. Okay, set of all even permutation. Remember the sign definition? We send cycle to 1 if it is even, to -1 if it is odd. Okay, good. What else? How about the kernel of exponential map from R plus to R cross? Okay, still remember this map or not? Sending x to e to the power x. Okay, so what's the kernel of this map? What's the identity in Rx, R cross? Huh? It's also 1. Okay, what is the thing that gets sent to 1? E to the what is 1? Only 0. Okay, so this means this is a singleton 0 set. Okay, singleton set. What else? Interesting one. So maybe look at this example, number 4. What's the kernel of absolute value map? Okay, or the norm function from C cross to R cross? So what's the length of a complex number that is equal to 1? It's a circle. What's that group? What's that group called last time? They satisfy a algebraic equation that is equals to 1. Right. So these are the roots of unity. Okay, roots of unity, which we call U. So this is a unique circle in complex plane. So U is the unique circle. Okay, so this is a complex plane, IY. Okay, and then Y, they are equals to 1 because of the length. Okay, because of the length. Okay, length of the complex number. Okay. How does this elements looks like? What's the form of this element? E to the I theta. Okay, e to the I theta. Okay. Yeah. E to the I theta. What else? Let me see. Okay, how about this one? So last time we wrote down a covering map, right? From R to U. Okay. So this means what? We have this circle here. Okay. We have a map from R, and then we wrap infinitely many times. Okay, we wrap infinitely many times. What is this map here? X to e to the 2 pi I x. Okay. So we have a real line, and then we map infinitely many times. Okay. So what's the kernel of this map? So what's the kernel in U? Root of unity. What's the composition in root of unity? Multiplication or addition? Multiplication. 1. Okay. So when does it equals to 1? When does it equals to 1? Just now we talked about the exponential map, right? Yeah. 0. Wait first. But here is what? What's the exponential here? Okay, so I think I need to remind you what is e to the I pi. So what's e to the I pi? Cos theta plus I sine theta. Okay, but we got a 2 pi there. So we got a 2 pi here. We got a 2 pi here. Okay, I mean this is a scalar. 2 pi. And then 2 pi. Okay. So when is it 1? When is it 1? When does this equal to 1? Integers. Yeah, only when it is integers. Any question? Question. So meaning where is 1? 1 is here. Okay. So when you wrap around this circle, right? When you start from 1 to 2, you wrap once. 2 to 3, you wrap another once. Okay, twice. And then 3 to 4, 4 to 5, 5 to 6, and then like this. Okay, you wrap like this. Okay, so 1 to 2, you wrap once. 2 to 3, you wrap once. 3 to 4, you wrap once. Okay. Okay, any question before we take a break? Yeah. Before we finish the class. No. Okay, if no, we'll see you on Wednesday.
这个还是你自己后来加上去了，这样如果我们没有这个，我们是不是看不出来？
哎，我没有跟你讲这个是什么 map， 你都不知道，对不对？
所以我们还是要这个才可以懂啊。
你讲要这个啊，当然咯。
这个妹子。